should have fixed the notes now, so it's a blank copy.
We have lab today?
We have lab today. No. I have one on Thursdays.
We have lab today?
Yeah, we have a lab final.
Lab final?
Yep. All right, let's get started. Sorry, I was grabbing your homework off of the printer. So if you can believe it or not, we are here at week 10. And so, yes, in answer to the question, we have our lab final this week. So of course, you'll just take it on your respective day, and it's within your best interest, right, to not talk about it so that the other class can't, cheat and get extra help. Yeah.
I didn't bring my lab. Do it like Thursday. It's not even today.
So if you're having lab, you need to do your lab. So right, there's a copy of all the labs online. I graded a bunch of labs, but then they didn't make it into the grade book. So I'm going to try to do that between now and lab. It's probably not going to happen. So it's probably going to be a mess, but I'll hand back what I have graded if you want it. I honestly try to make the lab exam such that I don't really think you need it, but you might want to reference it. But like I said, they're all online on Blackboard, so if you're missing one, I think that's enough of a reference, hopefully. So yeah, that will happen today in either your Tuesday or Thursday lab section. And then lab makeups, I want to finish them on Friday. So if you are missing labs Friday, I want them done, so we're not lingering into next week. Next week would just be kind of like emergency makeup if we need, but like I said, I really don't want to do that. I'm trying to get the grades finalized. I want the grades done kind of early. Yeah. So this Friday, I think the time we're tentatively thinking is starting around 11 a.m. So if you need to do multiple labs, you probably want to be there right at 11. If you have other scheduling issues, let me know. But please email me. I need to know what labs you're making up. The stockroom has to prepare, right? At least 2 of the labs are pretty sensitive. Both of the reaction rate labs are sensitive, so they have to make fresh solutions. So email me. Like I said, let's get that done. If you can't make it on Friday, let me know. We can maybe squeeze some in with the lab finals, but we want to get that done ASAP. And then on that note, check your grades. So check your grades. Like I said, I've been trying to get caught up on the grading. Blackboard is super buggy though. I don't know what it is. Like if you're entering a normal Excel sheet, you just hit enter and it goes down normally. For some reason, Blackboard doesn't do that normally. So I try really hard not to mess up and skip anybody's grades, but I'm obviously not perfect. Also, many of you are missing quizzes, so get those reading quizzes done. That will hurt your grade. And I'll try to update the thing. Your grade is like wildly inaccurate, right, on Blackboard. So I'll maybe try to fix that, but no promises. Like I said, last year I ended up just manually calculating it because it was way simpler to understand than trying to understand whatever the heck Blackboard tries to do. Oh, and then any last quizzes too, makeup quizzes, get that in. People are like missing assignments, so get missing assignments in.
When do we do makeup quizzes?
Anytime you can, like ASAP, like yesterday. Like we're at the things should have been made up by now point, right? So this is panic mode. We need to get everything in now because I'm also trying to like eliminate my grading because Historically, the end of the year has not been very good for me, and I literally work Friday, Saturday, Sunday, and stay up all night Sunday to get your grades in by Monday. I'm really trying to avoid that. So get things in ASAP. Because I'm also trying to go to a conference that weekend, so I will physically not have the time, yeah. So that's why I'm like, we need to make stuff up yesterday and now. So that being said, please get your papers turned in. So papers are due by the end of this week. I'd prefer them Thursday paper copy. I'm just much more of a paper copy person. But otherwise, email by Friday.
We're doing a paper copy, is there any sort of like formatting we have to follow?
I believe there were guidelines talking about like 12-point font and yeah, and all that good stuff, but it's pretty standard, 12-point font, all that stuff. All right, any questions, comments?
Is the final on Tuesday or Thursday?
Thursday. So we'll do our review as usual on Tuesday. And then, yeah, final on Thursday. And then, yeah, lab final is whenever your lab is. So some people have it today, some people Thursday.
On for the paper, so if you, I happen to gather papers that didn't really have the same format that the original scientific paper has with having experimented and concluded the hypothesis. On the actual rubric, it says that you need to have a section that you analyze through like conclusion and whatnot.
So we could talk individually, right? Because I said that was more of a loose rubric, right? Kind of very traditional. But I said that you could go off topic and
I
that,
want to make sure that.
yeah. But let's talk personally and just see how it fits in.
So we're probably going to cover this next Tuesday, review, but is the final going to be mainly covering the second half of the
Yeah, so the final will be mainly the second half. So no MOs will come back to haunt you or anything like that. We have plenty of kinetic material to test on. And don't forget about, right, acids, bases. Yeah, so we'll have plenty of materials, so none of that. I'm trying to think if anything is cumulative by nature, but yeah, I won't ask like geometry questions or hybridization this time around. All right, any other questions, comments? Yeah.
Is the final going to be fully open note or?
Yeah, so the final will be fully open note, like I've been doing. Yeah, I might make it more multiple choice. We'll see. I have to write it still, but yeah. It'll be open everything, so we'll continue to do open resources, especially for these chapters. There's a lot of equations. All right, so let's get into our acids and bases chapter then. And so you probably at least know like the basics of what an acid and what a base is. And so most people are familiar with acids, and you might associate a sour taste with them. You might think of lemons, right, or other citrus fruits. They also have the ability to dissolve metals. We've seen that with like hydrochloric acid or sulfuric, etc., right, nitric, on and on. And then, of course, they can neutralize bases. We've seen that with our neutralization reactions or even just playing around with our citric acid in lab. And then if you're using just the litmus paper, then you use blue litmus paper to test for the presence of acid, and then it changes it to red if it indeed is acidic. And so here are just some common acids. So hydrochloric, metal cleaning, ore refining, so right, a lot of metal extraction. Also the component of stomach acid. So of course that's why your stomach is able to digest. Sulfuric, that's used in like fertilizers or explosives, of course. And then it's in your batteries. also used for electroplating. So nitric, again, more fertilizer and explosives, as you can imagine, and other productions. Acetic acid, of course, you know that's just the chemical name for vinegar. So again, a lot of food preservation, obviously also used in manufacturing. Citric acids, of course, right, this is what we have in our lab here. Obviously, it's in citrus fruits, but it's also used to make candy. So oftentimes, chemists or like labs will buy citric acid from like bulk candy distributors. It's like a cheap way to get citric acid. And then carbonic acid. So of course, this is in your soda or any carbonated beverage. I don't have any LaCroix today. And of course, that just reacts, right? The combination of carbon dioxide and water gives you carbonic acid. Hence why we also had to flatten the soda for our right titration, if you remember, because we didn't want any carbonic acid confounding. And then HF, of course, this has a reputation in film for dissolving bodies, of course, used in industry, right, for metal cleaning and a lot of silicon wafer or silicon chip manufacturing. And obviously, right, you see the etching. And then phosphoric acid, so that's a biological buffer. And then you also have a small amount in sodas as well as preservation. Yeah.
So I understand that something dissolves when it's put into an acid. What happens if someone's put into a base? Does it just end up with a bunch of deposits on it?
So the base can also eat away at it.
So it dissolves in base as well?
Well, it depends what it is, yeah. But like, for example, that's one of the ways to clean like glassware that gets really messed up, we'll say,
Oh, right, yeah.
is,
And you put it in a drain, so.
yeah, well, you put it in a base bath, which is just isopropanol sodium hydroxide, and that literally it eats away at the glass, but it makes it super clean. Obviously, over time, right, that weakens your glassware, but yeah, from experience, if you silate something, you silate the glass and then have to put it in a base bath. Anyways, we work with nothing that nasty that requires base baths. But yeah, most like working labs will have a base bath for cleaning. And then acid baths, remember, they usually just don't keep those around because they're usually not to be stored. Yeah, so like aqua regia, for example, that can't be stored. So aqua regia is a super cleaning solution. So it's, I always forget the ratio. I think it's 3:1 HCl to nitric. And it's used to clean off like mainly metals. So this is like, you use that once you've like gone through all your organics, and then you can try aqua regia. The problem with this is, yeah, you're not supposed to store it because it has the potential to explode, which I've heard. Yeah, this has happened to other people that I know, not me, where they were just standing there and there was an explosion, and it was because someone had attempted to store aqua regia. So, yeah.
How often do explosions happen in working chem labs?
I mean,
Nice.
yeah, I mean, the problem with that is, right, no one wants an explosion, and it depends how big the explosion is, but you tend to hear about the explosions that
Do happen.
and like cause loss of eyeballs is usually what happens, or yeah, vision loss. Let's see, back when I was a grad student, like 2019, 2018, like right when I was going to graduate, it was actually an undergrad lab that they were doing. Someone was heating a thing, and you know how it goes. The minute you're like, nothing's happening, and then you take off your goggles and stare at your reaction, that's when something happens. And so, yeah, there was some vision loss in an undergrad lab. I'm trying to think of other big explosions. Big other famous explosions were like, I would have to look up how long ago this was. Fairly recently, I'll try to look it up. Someone was trying to do a glove box experiment, but they were like piping in hydrogen and oxygen to like do some sort of combustion thing, but then they ended up exploding the entire glove box accidentally. So yeah, it just depends like how big. The other culprit that usually gets people for explosions, or like baby explosions, is if you're doing like NMR tube reactions. So right, we've been talking a lot about all these mechanisms and blah, blah, blah. Well, part of what you do if you're trying to tease out a mechanism is like you freeze your reaction in this little NMR tube called a J-Young, which is pretty similar to like the apparatuses that they were doing. Oh my gosh. Sorry, apparently Jay Young is a rapper, geez. Just trying to like find what a Jay Young is.
Young chemistry.
Yeah, exactly. So it's just a sealed valve, but if you're not careful and you're not like thinking about what you're condensing, you know, if you accidentally condense a liquid in there that's going to expand to a gas, obviously at a temperature, then things go kaplooey. And yeah, there's a professor at the University of Minnesota who like damaged his eye doing that, and many of other people have done that. So yeah, you don't want any explosions. Let's just say that. All right, so I'll try to look at more explosion horror stories, but let's look at our organic acids. And so this kind of gets us into at least a small tease of organic chemistry and what this carboxylic acid group is. And so this is the carboxylic acid group, so drawn out, so this CHO-looking thing. And so basically any organic acid is going to have this group on there of the carboxylic acid, and then it's this proton here that's susceptible to deprotonation. And so then it just depends, right, how many carboxylic acid groups. Let's maybe look up a better picture of citric acid, just so you could see. And so, right, citric acid, if you remember, is triprotic, and there's our 3 carboxylic acid groups, so there's our 3 acidic protons there.
What does triprotic mean?
So remember, it has 3 hydrogens to lose.
Oh, okay.
So yeah, if we go back, so right, remember how we said it took 3 equivalents of sodium hydroxide to neutralize the 1 citric acid? Well, it's because of those 3 acidic protons right there. But then, right, we kind of rewrite it in this sense. So, okay, H3, so it's kind of obvious which ones you're deprotonating. So then with bases, so I don't know if anybody has ever gotten their mouth washed out with soap. That used to happen. I don't know. That still does. If you ever have, then you know that, right, soap tastes bitter, hence why that's a punishment. Obviously, you don't want to generally eat bases. The only exception would be, right, the tonic water with the quinine in there. And then otherwise, they feel kind of slippery. You probably know that with soap. You don't generally want to go touching the sodium hydroxide solutions, but
Also, like certain types of fruit that they have saponins in them, and they're too ripe to eat. One time, I think it was like a papaya or like a or something. I bit into it, and my entire mouth filled with soap.
oh, gross.
Such a weird feeling.
Huh.
It was exactly like this.
Oh, that's interesting. Yeah, I'm not familiar, but I don't know too much about papayas, honestly. But I could totally believe that. So yeah, that's interesting. And then, of course, they can neutralize acids, and if we were testing for it, right, they change red litmus paper to blue. And so table of common bases. And so we've seen a lot of these, of course, right, sodium hydroxide, potassium hydroxide, and then both of them, I think we mentioned it in here that they're used in soap production. They can be used pretty interchangeably. And then sodium bicarbonate, so of course that's just good old baking soda, another buffer, so it can be used as a buffer, antacid, or source of CO2. Sodium carbonate, water softener, can also be used in soap manufacturing. And then ammonia. So of course we've seen ammonia. This is again used in fertilizer and explosive manufacturing, but also detergent manufacturing. All right, so let's look at some definitions. And so this is just saying that we can't have a proton by itself. So basically, well, let's look at something simpler. So let's just say, right, we have HCl, and we often, draw its dissociation like so. And so all that we're trying to emphasize is we're not going to really have this, kind of naked proton here, just because they're not actually going to exist. So truly, what the form is when we write H plus is hydronium. So that's all that's saying. But like I said, they're used pretty interchangeably. And so you could think about how this mechanism, right, would actually work. So you would have to have water, and then action at the electron, and so then, right, deprotonates it, and so then we form hydronium and a chloride ion. So that's all.
Sorry, if you were to run a current through salt water, would it separate the two atoms in it?
Yeah, but you're still not going to have H plus. That's what you're saying. Right, so even when you perform hydrolysis, what you're separating it into is hydronium and hydroxide. Yeah. So like I said, everyone just uses H plus because it's, I like to say chemists are lazy. We use symbols for everything, but yeah, people just don't make that distinction. But yeah, you can't just have naked proton. So again, these are used interchangeably. Just kind of know that. All right, so now we want to go over kind of our definitions. And so we'll start with the Arrhenius. We'll look at the Bronsted. And then we'll at least kind of mention the Lewis definition. We probably won't see Lewis acids and bases here, but when you move on to higher level chemistry, then this would be the best way to analyze it. And so we'll start with the Arrhenius definition, and this is, of course, kind of historical too. And so, okay, well, the observation is that acids are substances that, when dissolved in water, produce H plus, or like we learned, right, formerly hydronium. So again, we're thinking of HCl or acetic acid, right, vinegar. And so, right, we can see that those give off a proton. And then bases, okay, we said that these are substances that produce hydroxide. So again, just thinking about the dissociation, or like calcium hydroxide, strontium hydroxide, right, on and on. All right, and so kind of the problem with that, and we can look at the Arrhenius theory here. So again, right, just looking at the basic dissociation. And then, of course, blah, 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 right, very simple. Acid-base reaction, make water. So we've seen that with our neutralization reactions. And so the problem with this, and you might already be kind of aware, is it's too narrow of a definition. So it doesn't tell us why, like, ammonia makes a basic solution, right? So there's no OH there. So where's the dissociation? And it doesn't explain how sodium carbonate or sodium oxide also makes basic solutions, even though they don't have hydroxide ions. And it also doesn't tell us why CO2 makes acidic solutions. And, right, it doesn't explain any other kind of types of reactions. So then we can go to the Bronsted-Lowry definition. We'll kind of look back and forth here. And so now Bronsted-Lowry tries to go a little bit further. So now it's saying, okay, well, acids are still something that when dissolved in water donates protons, and right, it still has to have a proton to donate. And now it's saying that bases are anything that accept hydrogen. And so now this will explain at least, right, our ammonia. So we can go back now and look at our Bronsted-Lowry definition in more detail. And so now this is just kind of our generalized reaction here. So right, we have our HA, so meaning it has, again, a proton to donate. And then we have these two little electrons here. And this kind of fits in better with the Lewis definition. But this is kind of hinting to us that, right, we have these lone pairs that are ready to attack and deprotonate that H+, right, and make what will be our conjugate acid, of course. And so we can start to get into the definitions too. So, right, our base picks up a proton and then becomes our conjugate acid, and then leaving, right, our former acid as with no proton and conjugate base there. Yeah.
Are you familiar with any chemicals that have like a sort of a gradient of acidity and alkalinity based on temperature?
Probably not based on temperature. I'm not sure about that. So then let's look. So now it tells us to write the ammonia issue. And we can look at this. And so let's just draw out kind of the mechanism more. And so this is where at least our geometry stuff comes into play, right? So you're not testing over it, but we can see, okay, we have our ammonia, with our lone pair. And then again, of course, water. And so now in this case, right, nitrogen is acting as our base. Action starts at the electrons. It's going to deprotonate our hydrogen. Oxygen gets the rest of those. And so, of course, now we form our ammonia. And then we're left with our hydroxide. So now this fits under the definition of, okay, we formed OH ions, and now we proved how that happens. And so again, we can pay attention to our labels here. So we have our base, and then, right, we knew it was a base because it wanted to pick up a proton. And again, right, kind of having those electrons was another hint for us. That means water's acting as our acid, since it donated a proton in this case. And then that leaves ammonium, right, as our conjugate acid, since it picked up a proton. And then hydroxide is our conjugate base there. All right, so make sense so far? Ask questions. Yeah, like it's pair basically. So then you kind of want to look at their conjugate acid-base pairs. So again, right, you have your acid, and then your conjugate base, right, is just missing your proton there. And it could even be as simple, right, as HCl. Well, your conjugate base then is chloride. And then, right, whatever our base is, we could use water as a base. And then make hydronium. So, right, so there's our acid-base species again. I mean, right, H2O, not so weird.
Is this a complete definition of an acid base?
So it's not the complete definition. So we can at least, right, mention our Lewis definition. And so like I said, we're probably not going to look too much at these Lewis base pairs, but we can at least look at kind of one classic example. And so the power of the Lewis definition, of course, is it's the most expansive, and then based on electron donors and acceptors, which kind of helps us with the Arrhenius one, right? Because like I was mentioning, well, look out for your base. Your base tends to have those two lone pairs anyways, right, to attack. But now with this Lewis definition, we can say, well, acids are substances that need or accept an electron pair, and bases donate. And so one of these classic examples would be this pairing. So we have BF3, so boron trifluoride, or really any boron substance. And then if we pair it with an amine or a nitrogen, I'm just going to simplify with ammonia here. So we have this sort of situation. And so, right, this is a Lewis base pair. Lewis acid base pair. And so this is what they're talking about with this. And right, so there's no like protons being exchanged by this definition, right? Nitrogen is just donating its 2 electrons, right, to boron to stabilize it. So that's our definition there of a Lewis acid base pair. And then, I mean, this goes down a whole vein of research too, because this is what people are trying to do, is make what's called frustrated Lewis acid base pairs, where you basically have this situation, but you want to keep them just out of range physically, so where they can't donate, and then the idea is hopefully they do cool catalytic stuff. Obviously easier said than done.
Is it like kind of like holding 2 magnets together?
I mean, kind of, although, yeah, I mean, magnets is more poles versus, right, you're trying to get some sort of electron action going. Yeah, but kind of the idea of you have something that's frustrated, wants to react, but can't. But yeah, like I said, we won't really deal with too much of this situation, but you should at least be aware. All right, so back to our kind of our setup here. And so again, like we were kind of seeing, we want to be able to identify these conjugate acid-base pairs. And like we saw, our original base picks up our proton, becomes our conjugate acid. And then our original acid becomes our conjugate base. And so it mentions the reverse reaction. And so this, right, just relates back to our equilibrium, depending on which way we're looking at our reaction. And so then you want to be able to identify your conjugate pairs. And so they only differ by a proton, right? So we're looking at ammonia and ammonium. So, right, we just added a proton. Or in this case, right, H2O and hydroxide, we remove a proton. So again, just reiterating that our base is going to accept our proton, our acid is donating our proton. So let's see if we can practice that. So just go through these two examples, right? Who's acting as your acid, who's your base, and then of course, from that, right, who's your conjugate acid, who's your conjugate base. So try both A and B, and then we'll go over them. All right, let's look at A together. So we have our sulfuric acid plus water gives us hydrogen sulfide or an H3O here. So who's our acid? So sulfuric, so this is our acid here. And so we could tell that, right, since it lost our proton to make our hydrogen sulfate. And so what's our water acting as then? Our base. And so then our hydrogen sulfate, what's this now? Conjugate, so what did it?
That became a base, I guess.
Yeah, so right, compared to the acid, it lost a proton, so it's our conjugate base. And then that means that our hydronium over here, again, compared to its pair, gained a proton, so what does that make it? Yes, so conjugate acid. Good. Questions on A there? So now if we look at B, so now we have this hydrogen carbonate ion plus water gives us carbonic acid and hydroxide. So hydrogen carbonate, does it look like it's an acid base here? Check what's happening though, because is it losing a proton or is it gaining a proton? So if it's gaining, then what's its role here? So it's a base. So right, acids accept electrons, but they donate protons, right? So in this case, it gained a proton. And then what is water then acting as in this case? Of course, this is our base, right? What does this have to be? Acid. And then, so that makes this now our what? So our conjugate acid, good. And then, of course, this leaves it as our conjugate base. And so let's just look at this, right? Again, we'll look at a similar scenario. So what if we had had this kind of issue? So what if we were looking at our hydrogen carbonate again and water, but then this time we made carbonate. So now what can we say about it?
Everything's going to be reversed. So that becomes your acid, and then the base becomes your acid becomes your base.
Excellent, right? And so do we see how, because you kind of have to look at the whole picture, right? So now in this case, it's still hydrogen carbonate, but okay, it went from hydrogen carbonate to carbonate, so we can tell it lost a proton, so good in identifying it was an acid. And then yes, that means that this has to act as our base, donating, or accepting, excuse me. So then we get our conjugate acid, and then of course, this leaves us as our conjugate base.
Does that only happen, you only label the two that in equilibrium reactions like this? Or
Yeah, well, I mean, essentially.
is the conjugate base or the conjugate acid and base always on the right side? Or does it have to be at a specific concentration?
Yeah, so usually it's always on like the product side, because then you could kind of rewrite it then and say, well, now we can look at this reaction of our carbonate plus, and it'd be more appropriate to use water, right? But then, okay, there we go again. So this is our base. So once it's on the reactant side, yeah, it changes back to base.
It has nothing to do with the relative concentration.
No, yeah. It's just where it is and what we're looking at with our equilibrium. So yeah, now that we've relabeled it, we can, reform our first step. Oh, back, now this is our conjugate acid again. All right, we made hydroxide, conjugate base. So yeah, that's something that you want to be kind of comfortable with, right? Writing these reactions kind of one way, and then understanding you could write it in the other direction. And we'll kind of tie in all our equilibrium as well with this. So
If it gets rid of one proton, it's
yeah, so if it's losing a proton, right, it's acting as the acid, and then it becomes the conjugate base. And then, yeah, if it's accepting the proton, then it's acting as a base, and it becomes your conjugate acid. And so just kind of watch out, too, for those acid-base pairs. So the other hint is, so right, your acid-base pairs can only differ by one hydrogen. And so what I mean by that is sometimes you have these questions that are like, what are appropriate acid-base pairs? And you're given, a bunch of answer choices that look something like this. But then which one of those is not appropriate?
The third one.
And so why is it not appropriate?
Differs by greater than 1 hydrogen.
Excellent, so 2 hydrogen difference. So yeah, just watch out for that. That's a common trick on exams and questions is exactly, they'll put something with a 2 hydrogen difference, so your acid-base pair is always going to be your 1 H difference.
If you have say you have like citric acid on one side and then a base with 3 modes for equilibrium, would that count as an acid-base pair? Or do you have to have one?
Well, it's their, so it would be, right, the citric acid, what's citric acid's formula? So, right, citric acid is H3C6H5O7. So then, right, the acid-base pair is each subsequent hydrogen loss. So H2C6H5O7, right? So there's one acid-base pair. Then you could do the next one. So it's just with each subsequent deprotonation.
So it's kind of like a formula system or what it was called?
Yeah, I mean, if you want to think of it that way, but again, you're just making your pairs with as long as they have a 1 hydrogen difference. And so that's where like the different equilibrium constants will come into play later. Oops, sorry, I messed that one up. I just wrote it in reverse for some reason. But yeah, all those are appropriate, right, acid-base pairs. And then we don't know what base deprotonated them, but right, you could do your hydroxide water. Does that make sense for the acid-base pairs? And then we'll probably take our break, but I did want to point out, so I'll probably go and try to print out this chart for you during the break. But this is a nice chart because this has all the acid-base pairs. So we'll kind of go over it more in detail after the break probably. But we can kind of see our strong acids here up top. And if you kind of remember, there are 7 of them. And so all that means with our strong acid is they undergo complete ionization in water. And then, of course, we have all the respective acid-base pairs along this line here. So that's super useful. Like I said, I'll try to get this printed for y'all. But let's go ahead. We'll take our break. And then we'll pick back up with the strong versus weak stuff and keep looking at our equilibrium. Oh, yeah, you can hang on. Yeah, so that would look over some of you guys, right, because remember the solid one, shouldn't be part of the expression, the same sort of thing, as either it should be like a polarity with the concentration or partial pressure. Yeah, but I'm saying you got a solid there, so that would be part of the expression. Correct. Yeah. So then for this, right, this is a liquid region, that's a solid, the gas would be the only one that matters concentration and not force. Yeah. Yeah, and then eliminate anything else from the expression. Since again, the concentration won't change. Wait, all back from break. And so maybe I'll post some of these CNN articles back to the topic of explosions, since that's always a fun topic. This one is just lessons in lab safety, so this could be interesting. It's a podcast, but it's also a transcript. I was just kind of reading over it, some things that I wanted to point out. This is a distillation lab setup, but you know how I always say, like, or I don't know if you remember, like, there's this bad, I think it's a horrible graphic in your textbook where it's like open flame distillation. But this actually points out where they, did used to do these distillations over a Bunsen burner. And then look, lo and behold, it caught on fire. So just what you would expect, right? Obviously, you're trying to distill a flammable organic liquid over an open flame. You have some, it gets compromised at the joint, which can happen really easily, right? You guys saw that when you even distilled your Franzia. It could come out from the joint potentially. And so, yeah, caused a fire. And apparently someone reached through the flame and like cut it off, you know, probably cut the gas or something. But obviously, just thinking about that. And another funny story in here that I thought was interesting, if I could find it now. Blah, 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 blah. Oh, this was a good one. So somebody who worked with explosives, and this goes back to why you should label your containers. But apparently they had some baking soda in containers for spills, pretty common. And so there was a beaker with some white powder in the back of the fume hood, you know, didn't know what it was. Then they set off this explosion, which sounds cool in itself. Some sort of strontium peroxide compound, and it's making all these pretty sparks and everything, and then next thing you know, kablooey. So the sparks went into the unknown beaker, and so the analysis later, I mean, this is kind of crazy, they like blew up their entire fume hood, which is pretty crazy. And so yeah, it was not baking soda, it was lead azide, and azides are pretty notoriously explosive. So yeah, if I remember, I'll post that so you can kind of read. There's also, I could also post, this is a good reflection. This is the horror story that I always give at the beginning of lab, like first quarter, the whole, you know, the person set themselves on fire because they violated like a whole bunch of safety protocols. So this is just kind of the reflection on that. So it mentions, right, the T-butyllithium and trying to use the plastic syringe and all that. So that just goes into safety protocols. Kind of interesting. And then this is the explosion I had mentioned. This was the big one. It was in somewhat recent memory. So it was 2022 when that person apparently had exploded themselves trying to do that hydrogen-oxygen experiment. I don't know if there's an update on this, because that would be interesting, because at the time this was written in 2022, they still didn't know quite why it exploded. They thought this was a well-established procedure of, you know, putting these gases into the glove box and doing their thing. But, you know, obviously something happened. So anyways, safety is always good to be aware of. All right, so let's look at our strong acid and strong base. And so this can kind of go into safety too, especially when we think about like fluoride. And so fluoride is always troublesome. And we'll get into why it is. But let's just start with our introduction. And so again, we're just kind of defining what an electrolyte is again. So, okay, we said our strong acids are defined as strong acids because they have complete ionization. And so again, when we write their dissociation in water, I'm going to use our single arrow to show that it goes all the way to completion, right? So same thing with nitric acid, goes all the way to completion, right, disassociates. And so then the weak acid is, again, has nothing to do with how dangerous it is, but rather this equilibrium. And so now we get into the danger of HF and fluoride. And so HF disassociates. We have an equilibrium. Again, all we're saying is some of it is disassociated, some of it is not. But then let's think about what can happen and what some chemists, especially if you're a young chemist, what you may not realize. And so this is a danger. So if you have fluoride in solution and you have some water, so right, pretty common that could happen. Well, now what's going to happen? Well, we have our fluoride here, right? It can pluck off some water and reform HF. And of course, we'd also form our hydroxide in this case because we're starting with fluoride and water acted as our acid. But this is the danger. So now, right, we've reformed HF. So anytime you are making something or you might have some fluoride salts formed, then it's always a good idea, right, to neutralize it, throw some extra baking soda in there to get rid of any potential HF that has been formed.
Is there anything that reacts with hydrogen more intensely? Or is fluorine is a really reactive element? Is it like the absolute most reactive element of hydrogen? Or something else?
Yeah, I mean, I wouldn't say that. Plus, it depends, like, what pathway it's going through is really what that's more getting into, like, thermodynamics, I think. And so then, right, same thing applies for our strong base. So all these tend to be, right, our ionic compounds. So calcium hydroxide, barium hydroxide would be in there, right? Obviously potassium. I'll throw in there rubidium, right? Magnesium. Okay, so all of those tend to be strong electrolytes, again, fully disassociating. And then versus our weak electrolyte, so again, you're only going to have partial ionization. So we could look at our ammonia again. So plus water gives us some equilibrium, of ammonium. And so it can go back and forth in solution. And again, right, equilibrium, all that means is we could, right, start with our ammonium, react it with water, and reform our base there. And then, so here's some trends. And so these trends, they kind of help us see our overall picture too. And so this is kind of our statement here. So the stronger an acid is at donating a proton, the weaker the conjugate base is accepting a proton. And so let's kind of dissect what this means. And so I like to take it to the extreme of HCl, right? And so basically what we are saying is, okay, the better this acid is at donating, so okay, HCl is a strong acid, it's really good at donating, then the weaker the conjugate base is. Well, I would say, right, that this conjugate base is so weak that it cannot reform. Right, so then we can say, so chlorine plus water, right, is not going to give us HCl. So it is, right, that poor of a base. And obviously then if you have kind of a weaker base, and we can go back to, again, HF, since that's a good one we're looking at. Well, in this case, right, well, it's not as strong as donating, and that means that this fluorine can then, right, accept our proton, just like we saw. So yes, it can reform.
What makes them better and worse?
Well, you could think of the equilibrium argument, right? Because that's really what it is. It's kind of an equilibrium argument in that if your equilibrium, right, it lies all the way to being separated, so then it's not favorable at all for chlorine to act. But that's part of why it is. It's just it's so weak of a base that it doesn't have the power, right? Because you can think of it from like electron attacking mechanism, but it just doesn't have the strength basically. But yeah, it goes back to this equilibrium definition. That's kind of the best way to see it. And then, so again, this is kind of just a general trend that you'll notice. So the more oxygens, the stronger the oxy acid. So sulfuric versus sulfurous.
Is an oxyacid any acid of oxygen?
Yeah. So, and then in this case, right, nitric is stronger than nitrous acid since it has 3 versus 2. So you'll notice that. And part of that just has to do with the stabilization. So if you have more oxygens, they're better at stabilizing a charge. So that will help lead to those stronger oxy acids.
Is that string is an oxidase? Is that what the term is?
I'm not sure. I'd have to look at that. Probably not, but. And then cations tend to be stronger acids than neutral molecules. And so this is where I kind of add, well, cations, right, are going to be your acids if they are going to be anything, right? And then your anion, if it's going to be anything, is going to be a base. And so this should just follow with those electron, right, donating and accepting trends that we've seen, but this is a good reminder. So, okay, so now we're saying, yes, if we're kind of thinking of those trends, our cation is a stronger acid, so comparing hydronium versus water. And then, right, it mentions that our neutral molecule is a stronger acid than an anion. Well, that kind of makes sense with our trend. And again, thinking that our anion is going to be a base, since anion's probably going to donate our electrons. And then obviously, right, it mentions the base strength being opposite. All right, so I printed this out, so grab yourself a copy either now or on the way out. And again, this is your conjugate acid-base chart. And so this is kind of helping you. So now you can say, okay, if this is an acid, I know it's going to completely disassociate in water. It tells me so here, or I could also remember, right, that these are my strong acids. And then, of course, across is the corresponding base. We can see that, right, differing by a proton. And then this has the hint here. So, right, what it's saying, that they do not undergo base ionization in water. All that's saying, right, is that it's not going to pick up a proton, right, and reform the acid here. Because, again, the equilibrium lies all the way to the right, so they will not reform. So these are not good bases. And so we can see that too with our little arrows. So our strong acids are at the top here, and then bases, so these are weak bases, or obviously, right, really poor bases such that they're not bases. And then we start with water, which we'll mention as amphoteric and what that means. And then, of course, increasing base strength there.
Is there any definitional difference between basic and alkaline, or is that basically the same?
Yeah, that's the same word. And so again, this is useful. You can see your conjugate acid-base pairs like carbonic acid and hydrogen carbonate, and then hydrogen carbonate and carbonate. So that might kind of help you there. All right, so now we're getting into the equilibrium. And so now we can kind of see where our Ka will come from. And let's actually, before we start looking at Ka, let's look at what it means. And so now we're getting into, right, relating our equilibrium expressions, and then basically now looking at our acid case, or we could look at our base later. And so we can kind of see what's going on, and this will give us, right, our general form. And so we have, I'll just kind of rewrite it, right? So we have our whatever HA, so obviously this is acting as our acid plus our, and then we're always going to be doing these ionization constants in water, right? And so water can act as an acid or a base, which we've kind of seen. And then, right, remember what we had said about including different things in our equilibrium expression, right? So this is a liquid here, so it's the entire medium that it's being run in. So that's why it gets excluded, right, from our equilibrium expression. And then, right, so just finishing up, and I'm usually lazy, and I just put H plus A minus, and then, right, this gives us our equilibrium expression. So just like before, products over reactants there. So that is our Ka expression. And so now that we have this, right, we can think about what this means and go back to what this was saying of this Ka. So again, right, I'll kind of rewrite it. So we have our HCl plus water, we should write it properly, goes to H plus chloride. And so now we're saying, obviously, right, our strong acid is completely disassociated, right? This is what the expression would look like, except our Ka is much, much, much greater than 1. So again, that's why, right, our equilibrium lies all the way to the right there. So 100% ionization. So, right, our Ka will basically be infinity or very large. Again, strong electrolyte. And like we mentioned, so if we have, let's just say, right, we have 1 molar concentration of HCl, we can, of course, right, know that if it disassociates, we have 1 mole concentration of H plus ions, right, and 1 mole concentration of chloride. So that's all that's saying there is, right, our concentration of whatever our substance is, HA equals H plus, and so we can calculate, right, our pH later. And so then here are strong acids again, so they just match up here. And so now we can understand, right, this weak acid better. And so again, we could put it in the context of HF. So again, we're saying HF in water, right, disassociates to make H plus or hydronium and fluoride. And then, of course, right, it has some sort of Ka equilibrium constant to show this over HF. And so we could look up, right, this number. And so you have a few organics down here. Otherwise, right, you can ask Google, of course. You may have slight discrepancies. And so let's find HF here. So HF, and then, right, it tells us the Ka, so 6.8 times 10 to the negative 4th. So, of course, we could, you know, solve for whatever we're interested in, whether it be equilibrium concentration. And so, again, we kind of saw that. So, right, we can't just assume that whatever we're putting in is the strength of our H plus. And so just like you did in lab, right, you had to solve for X based off of your Ka, an initial concentration. And so then the other thing that you want to be kind of aware of would then be the KB constant. And so let's kind of look at this, right? So if you have your HA, so let's kind of rewrite this, right? So we have HA plus water gives us A minus plus, I'm going to shorthand as H plus for simplicity. So again, giving our Ka statement of A minus over H plus over HA. And so then we just want to be able to take this for the base, right? So again, you're kind of thinking about who's acting as what now. And so we could think of it in a few different ways. So we have, right, our KB expression. So now we have our base, so let's just do A minus plus H2O gives us, actually let's not do A minus. We'll skip to base here. So right, base plus water gives us HB plus hydroxide. And then, of course, we can express it. So then, right, our KB is going to be equal to, so HB over hydroxide over base. And so all this is to say we can kind of go back and forth between HA and HB. Oh, let's get into that a little later. So we'll hold on to this thought for now. And so let's just continue with our equilibrium. So like we said, okay, the farther the equilibrium lies towards the product, so stronger the acid or the base. And so, right, we remember that. This is just like our equilibrium stuff. And so again, putting it in context, we have this table of a few acids. So the stronger ones are at the top, right? Their Ka is larger. And as we go down, right, their exponents get smaller. So we have benzoic acid. Here's acetic acid for context. Hypochlorous, right, goes down to 10 to the negative 8. And then phenol here. So phenol is a really, really weak acid. So 1.3 times 10 to the negative 10 there. So again, just kind of giving you some context. And so then, right, obviously it makes sense. The larger the Ka value, the stronger the acid there.
Most acid reactions or acid-base reactions are exothermic, right?
Yeah.
Are there any examples of endothermic ones?
I mean, I don't have any off the top of my head, but. All right, so then kind of picking up some of the pieces here. And so like we maybe have noticed is there's a few special things about water. And so first of all, right, we may have noticed that water is amphoteric. And so that just means that it can act as an acid or a base. So right, that there are other substances that are amphoteric as well. And so the other question is that there has to be some ions present. And so what happens, and kind of what they discovered, is, right, there's some amount of this autoionization. And they show the process here I'll just kind of draw it out mechanistically. But basically, right, we're saying that 2 out of every 1 billion water molecules does this in solution, right, naturally. And so they're just kind of staring at each other. And then one of them can attack. And of course, right, then that forms hydronium and hydroxide in solution. And so basically, right, when they're trying to puzzle out pH and all this, it was first discovered that, okay, if you just have neutral plain water, they found not only does this solution have hydronium and hydroxide ions in it, they found that they were equal in, like I said, neutral water. So this is important and kind of teasing our pH scale. But the concentration of both of these was found to be 1 times 10 to the negative 7 molarity, again at 25 degrees Celsius. So for our purposes, right, we won't really care about temperature. This could fluctuate slightly based off of temperature, but not enough to be of significance for us. All right, so then the next kind of key relationship is that the product of these two concentrations is always this. And this is just our Kw product constant. And again, this is a definition. And so it'll be 1 times 10 to the negative 14, again at 25 degrees Celsius. And for our purposes, right, we will always take it as such. And so again, just kind of maybe write that relationship. So again, the concentration of these two multiplied always gives you that. So again, that's our Kw. And so part of what this is saying is, of course, as one increases, then the other must decrease, right, so that they stay constant. So they're inversely proportional, right, since Kw is constant. And then, right, they're multiplied same side, so they have to be inverse. And so then that's the next thing about solutions. So, okay, well, all solutions have some concentration of H plus and hydronium. And so now we get into our definitions. So neutral solutions have equal amounts. Acidic solutions will have larger hydronium values. And then if it's basic, we'll have greater hydroxide there. So you can kind of look at that. So before we go on to the next part, just see if you can look at these exponents and figure out if it's acidic, basic, or neutral.
Can you go up just a little bit? Thank you.
All right, so what are we thinking? So it asks us to calculate our hydroxide. And so we can, oh, I didn't fire up my calculator. And so, of course, we can just use our relationship if we need of hydronium, or right, H plus times hydroxide concentration gives us Kw, or 1 times 10 to the negative 14. So what do we get for our hydroxide concentration for A?
It has to be a lot higher because the hydronium is really low.
Well, what does that have to equal, though?
1 times 10 to the negative 14.
So then, yeah, do the math for me.
Wait, I had it.
So divided by 7.5. And you could do, right, some mental math. So you kind of know what order to expect it on. So, right, I'm kind of thinking it should be 10 to the negative 9, maybe, roughly. Negative 10, I was a little off. So 1.33 times 10 to the negative 10. And so then what is this telling us? Acidic, basic, neutral?
That's going to be
Which is greater, though?
it's going to be acidic.
Yep, acidic, right? And you're also looking for your kind of magic number of 1 times 10 to the negative 7, right? So if it's greater than that, so negative 5 greater than negative 7, so it has to be on the acidic side there for our hydronium. And then, so what do we get for B? What's our hydroxide concentration? That's right, just plug it into this formula. What do we get?
Where did you get that from the negative 14?
Remember, this is just the definition. So we're kind of teasing out the pH scale if you haven't noticed that yet. But yeah, this is just our definition of the KW. So basically, right, that was how they first established pH, was like they're trying to measure the concentration of stuff. So this is just by definition.
I got 6.67 times 10 to the negative 6.
So 6.67 times 10 to the negative 6. And so now we're looking at this, right? We got our hydronium is negative 9, hydroxide negative 6. And so is it acidic, basic, or neutral? Right, which one's greater? Basic, excellent, and chat agrees. And then what about our last one? What do we notice about this number here?
It's perfectly neutral because that's the number that's expected at neutrality.
Excellent, so it's neutral, and then, right, we don't have to do too much math, or at least we can do mental math for sure on that one. And so yes, neutral. Excellent. And so that was a good exercise. Before we kind of tease our next thing. And so, right, maybe this isn't the most intuitive to try to figure out which is bigger, which is smaller. And so you're probably used to this pH measurement. And if you remember, now we can have our formula formally introduced to us. We've seen it in lab, though. Sorry, I'm trying to change my color. And so we have our expression here. So our pH is just the negative log of our hydronium concentration. And so that gets rid of our exponent there. And so we could plug it in for one of these. So again, if we want to calculate pH, let's do B. So negative log, and of course make sure you're on base 10 with your calculator. So even if you think you know how to do these right, make sure you practice. Make sure your calculator's in the right base, although usually not an issue unless it's like a financial calculator usually. And so now we have our pH, so 8.8, so that's going to be greater than 7. So that's telling us, yes, it was basic, just like y'all had surmised there. And we can, of course, go in reverse. So if we know the pH, we can determine our concentration. So just take 10 to the power of the negative pH, gives you back your concentration. And then we have a nice just kind of scale here for reference, just so we can put things in context. Again, your stomach acid is a pretty low pH of 1 to 3. Limes and lemons, also very low, right, 1 to 2. That's also why, like, you know, they say you shouldn't maybe suck too many lemons because they'll wear off the enamel on your teeth, or like you shouldn't eat a lemon and then go brush your teeth right away, because again, that'll weaken the enamel. So same thing with soft drinks, right? All those can weaken your enamel. Even wine is pretty acidic, considering. And so then apples, peaches, cherries, they start being less acidic. So beer, right, is slightly acidic. And if you brew, I'm sure you try to keep your pH pretty constant. Once you find the good pH, I'm not a brewer, so. And rainwater tends to be a little acidic, so 5.6. Human blood, you know that has to be kept right at a tight buffer. So your blood is a buffer, 7.3 to 7.4. And again, right, necessary to be in that tight range for all your good biological functions. Egg whites are basic. And then milk of magnesia, maybe you've taken this, right, for an upset stomach. So that's basic. That's how it's supposed to work. And then, right, ammonia is going to be pretty high. And then obviously, right, sodium hydroxide is 14.
Is it possible to have a negative pH value instead of logarithm?
Yeah, it is. And those would be like super acids. So yeah, that's like a research field. What's his name? I'm totally blanking on the guy's name. Christopher Reed is he does a lot of super acid research, or at least he used to. He's pretty famous. I think he's retired now, but yeah, he made a lot of crazy super acids. And so again, we've kind of been teasing this, and now we have our pH scale. So right, you can kind of see why this is 0 to 14. So it's related back right to our KW product constant, so hence why it has to generally go from 0 to 14. And then obviously the lower the pH, the more acidic the solution, the higher, the more basic. And then obviously it's logarithmic, so it's a factor of 10 difference in acidity. And so, right, you can just see that a pH of 0 is 1 molarity. All right, so calculate the pH then and see whether it's acidic, basic, or neutral. Don't forget your other relationship, right, if you need it.
number of significant figures for pH?
For pH, so with your concentration, if it has 2 sig figs, you add 1 more sig fig to the pH.
So in this case, you have 2 under after the decimal.
Yeah, or 3 total. So then what do we get for the pH of A then on that note? Nice.
3.7?
Yep, so 3.7 or 3.74, so give it the extra sig fig. And then, right, you can always kind of sanity check yourself, because if you look at the exponent, it should be pretty close to your pH. So, right, -4, about 4, so that looks good. And then did you say if it was acidic, basic? So acidic, basic, neutral?
It would be acidic, right?
Yeah, so acidic. And then Chet agrees. And then, so this one, there are 2 different ways to solve it. So you could, right, plug it into here to get your hydronium concentration first. So that's probably the expected way, since I haven't shown you the pH formula, or POH. So POH is just a negative log concentration of hydroxide, which we'll go over formally in a second. And then you can also take pH plus POH is equal to 14. So either way, you could do it. I'll do it the other way just to show. And that's kind of the nice thing about this pH stuff, is it all should check out. So I'll do it the long way, so solving for our hydronium first, and then negative log of that. And so do we all get about 12.1 for our pH? And then acidic, basic, or neutral? Basic, excellent. And again, if we had gone the other way, so we could do negative log of this 1.3 times 10 to the -2. So that gives us our POH. And then we can do 14 minus that. And that also gives us our pH. All right, so then, here's the reveal. So now you have more expressions. So yes, now we have POH. And so, right, less commonly used, but we can still use it. So POH, like we mentioned, was just the negative log of hydroxide concentration. We can also, of course, go in reverse, right? If we know our POH, then we can solve for hydroxide concentration. And then, of course, note the scales are going to be opposite. So if we have, right, pH goes from 0 to 14. Now POH has the most acidic being 14, and then the basic being 0 for POH. Again, right, thinking about your concentrations. And so like I teased, so this is back from our KW product constant. And so we can just say we have this relationship of pH plus POH gives us 14. Here's just a quick derivation, right, why this is true. So we had our KW product constant. Then we take the log of both things, right? So now, or negative log, we should say. So negative log of this is just 14, right? You can plug that into the calculator. And then the negative log of hydronium and the negative log of hydroxide, right? We just distribute that. And, that's by definition pH and POH. So that's where it comes from. And again, right, we're appreciating our scale. That's why our pH scale is, again, from 0 to 14 there. And then other things we should note, I forgot to say this explicitly. So we have our Ka and also our pKa. And so similarly, right, that has a relationship. So our pKa is just our negative log of our Ka. And so you can see, right, the smaller the pKa, the stronger the acid, which is kind of confusing. So just remember that expression here.
In a pH and pOH and pK, how it's like parts hydrogen and parts hydroxide.
Yeah, I mean, I guess you could think of it as such. I'm not really sure why they have the P. All right, that's probably a good place to stop. So we'll pick up on Thursday, so we'll talk about buffers and then looking at our salts as acidic, basic, or neutral. All right, so don't forget to pick up the handouts. I have the homework and the other sheet. And then, yeah, don't forget lab final. So if you have lab today, we'll do that.
Would you like me to make up, when would you like me to make up, last week's lab?
Hopefully on Friday.
On Friday, I can do that. Should I wait to do my lab final until I finish that, or?
No. Yeah, you won't need
I
it.
forgot to turn this in last week.
Oh, sweet.
And then, is it too late to turn this in still for extra?
No, I haven't. I
Okay.
haven't gone through those.
Perfect, thank you.
Yeah, so I'll put this in this file, but yeah, I need to look through these soon. All right, any other questions before I end the stream?